All right, welcome to CS4510, L07A. The topic of today is non-context-free languages. So recall where we are in the class. We have proven that the languages decidable by DFAs are equivalent to the languages decidable by NFAs, which are equivalent to the languages decidable by regular expressions, which are equivalent to the languages decidable by GNFAs, and also, let's just put that in there, regular grammars, and so on. And then we showed via the pumping lemma that there were some languages which were not regular. And we said we were able to produce those languages or describe them by context-free grammars. And then we were able to talk about PDAs and say that the languages that are decided by PDAs are in fact equivalent to those decided by CFGs, right? Languages that are regular include things like A star, right? A star, you have any number of A's, right? Languages that are context-free and not regular include things like A to the n, B to the n, where n, the number of A's must equal the number of B's, right? Now, the thing with these kinds of, the regular languages are so simple. They are highly patterned. They're extremely, extremely patterned. And I think that there's an exercise in the homework that's something like, given a few strings, you can determine all the other strings in the language. So like, if I give you a few strings accepted by a DFA, if that few is enough, it turns out you know the rest of the DFA. That's how patterned the regular languages are, is that given a few of them, you can determine all of them. In some sense, they're the opposite of a random language. Context-free languages, we know, are languages that are not so simple because they require at least a little bit of memory. Any constant memory program basically is analogous to a DFA. So the fact that the stack must be used a little bit here means that they're context-free, not regular. But it turns out that the context-free languages are still patterned in such a way that we can say things about them, and we can still use the pattern that they hold to describe what a language is or isn't context-free. And the canonical context-free, non-context-free language is somewhere out here, which would be A to the n, B to the n, C to the n, right? So that's such that n is a natural number. Think about how those kind of are generalizations of each other. In some sense, the context-free languages allow you to, okay, I can match the number of A's to the number of B's, but I can't do anything else, right? And think about how you would try to decide this with a stack. You would push in the A's, and then you would pop with the B's, but now the stack is empty, so how are you gonna match that to the C's, right? It turns out there is no push-down automaton for this language, equivalent, there's no context-free grammar for this language. There is no way to generate equal number of A's, equal number of B's, equal number of C's. And the way we're going to be able to prove that today is by the fact that we will have the pumping lemma for context-free languages. Essentially, both context-free languages and regular language have a kind of periodicity to them, in the sense that a pumping lemma for the regular languages was like some X, Y, Z, and then actually this goes, all right. If the computation is long enough, there must be some loop that's taken by the pigeonhole principle. And so there's some substring of each long enough word in a regular language that can be repeated arbitrarily many times, right? So in some sense, longer strings are simply copies of, are built upon shorter strings with substrings copied in between them, something like this, right? So they're highly periodic, and there's a lot of pattern in regular languages. There's similar pattern in context-free languages, but where are we going to find that pattern? So we have to kind of look towards the computation. One thing we could do is say, oh, well, what if there's a repeated state on the computation of a PDA? And it turns out you can derive the pumping lemma using the definition of PDA, but that's very tedious, very annoying. So let's go with the context-free grammar definition. There must exist some sort of recursiveness for long enough strings produced by grammar. And that is going to basically come from the parse tree. So recall if we have a grammar of the form, let's say S goes to ASB or epsilon, we can produce the parse tree for such a string. Let's say S goes to, let's say, ASB. And then let's say this S is going to go again to some ASB. And let's say S is going to go again to ASB. And then we're just going to have S go to the empty string, right? Something like that. So that produces for us, this is the example of the parse tree of, given this grammar that produces A to the n, B to the n, this is the parse tree for AAABBB, right? In some sense, this is a visualization of the computation. It doesn't maybe tell you what order productions are applied in, but it tells you how to get which productions to apply in order to produce a specific string, right? But if you notice here, importantly, now this is a simple grammar because there only is one non-terminal, but S is repeated multiple times in the computation as we go down. So this string is of length 6, but the rules here are like length 3. So if the string is long enough, essentially, here's the quote-unquote pumping part. The non-terminal in the tree on some path downward is going to be repeated twice. That's kind of the idea. And let me just give you the photo. Right. So suppose we have S, right? We have some non-terminal A, and then because the tree is quote-unquote tall enough, we have the non-terminal A go twice, right? Something like this. So if the tree is tall enough, then a non-terminal can be repeated twice. So what's the height of the tree necessary to have a non-terminal be repeated twice?
N plus 1, where
Yeah.
n is the number of terminals?
Yeah,
Non-terminals.
so if the parse tree height exceeds v plus 1, then some non-terminal is repeated. Now, the next part that's going to take us some difficulty is like, we don't care, how do we get the parse tree from the grammar? That's going to be a little difficult. So instead we're going to say, if the string is long enough, similar to, analogous to the previous pumping lemma, so we have to argue about the string. So let the portions produced here be, let's call this U, let's call this V, let's call this X, let's call this Y, let's call this Z. So if some non-terminal is repeated twice, then we could say that S produces, through 0 or more steps, something like UAZ. Do we all see where that comes from? Some stuff happens here, and these get casted down. Some stuff happens here, those get casted down. Let's call those U and Z. And then A is something else here. But then, because A is repeated twice, we see that in the computation here, we get A can produce in 0 or more steps, VAY, but then also A can bottom out for just some string X, right? Do we agree with that notation, right? Where S here is produced by this grammar, and this is U, V, X, Y, Z. Question so far? Okay, well, what's our quote-unquote pump here? We can do what's something that's called a surgery on a parse tree. So the surgery will look like the following. If we take this photo, and instead of applying this sequence of productions, then this sequence of productions, and then this sequence of productions, let's just apply this one, and then this one. So what is that going to give us? Visually, we're going to have something that looks like this. Right? So instead of saying A, and then we have a V and a Y produced here, since X can just produce, since A can just produce this X, just in the computation of S, we could produce a different string by just forgetting to produce this VXY part and instead just produce X, right? And similarly, we can choose, if these are the sequence of productions that are done, instead of doing this one, and this one, we can just do this one, we can do this one twice, and then we can do this one. That would correspond to something that looks like this. I'm not an artist. Sorry. There we go, okay. There we go, okay. This part is gonna produce U, this A is gonna produce V, and this end part here of S is gonna produce the Z, and then A here is gonna produce also the Y. But instead of here, A producing X, like that goes here, we're gonna cut this part out and copy and paste a version of that right there. So what that's gonna give us here is VXY. Right? Do we see why that's true? Just kind of proof by picture. So what's basically our version of the pumping lemma? If U, V, X, Y, Z is an element of L, and L is a context-free language, then for all I, what must be an element of L? What string is produced by this parse tree?
UXZ.
Correct. This is UXZ. What string is produced by this parse tree?
UVXYYZ.
So for all I, what can we say is produced by, if UVXYZ is in L, what can we say for all I? It must be in L.
U to the I, X, Y to the I, Z.
Correct. Right? There are conditions here. This UVXYZ, this S portion must be long enough, quote unquote, and other things. But we'll derive those exact conditions. But this is basically the spirit of the pumping lemma as we have it. If the string is long enough and certain conditions are met to get the parse tree, the height that we want, I mean, then it just works out nicely for us. Okay. How are we going to derive the conditions of this, right? So we need to say, we can't argue about the parse tree height. We can argue about the length of the string as a function of the parse tree height. So let G be in Chomsky normal form. This will simplify things a little bit. So therefore, we only know we have rules of the form. A goes to at most 2 non-terminals, or A goes to a single terminal, right? If G is in Chomsky normal form, what can we say about the length of, the max length of the right-hand side is 2, right? So, if the parse tree has height, let's say h, then the max word length it can produce is some s less than or equal to what height? What is the largest string that can be produced by a parse tree? Given that the parse tree, let's say I tell you that it has height h. It's exactly h long. What is the largest word it can produce?
2H.
Correct. I'm actually asking you, how many leaves does a binary tree have? Right? Now, why is it less than or equal to? This isn't a worst case. It could be the case that the first non-terminal goes to 2 non-terminals, and those go to 2 non-terminals, and something really serious. But it's not necessarily true that this is like tight or anything, right? So we want to ensure, again, that the parse tree is height greater than equal to v plus 1. The height is greater than equal to this. So if the length of s is greater than or equal to something, then the parse tree height is greater than or equal to v plus 1. What should the length of s be to guarantee that the height exceeds this? This is a tough one. At least I've worded it. This is a tough one. If S is this short, then its tree height is at most this. So I'm saying if S is longer than something, its height must also be longer than something.
2 to the h plus 1?
Yes. Where does the plus 1 go?
Uh,
We'll say 2 to the V. Is it here or is it here?
I want to say the exponent?
Well, it's actually going to be on the bottom. So this is not a very important detail. In fact, it's going to make the pumping lemma less useful. So we're going to just say right now that if the pumping lemma is here. The 1 plus 1 is there, right? If it exceeds this depth, so if the string exceeds this length, it can't have a parse tree of height 2 to the h, as we've said, right?
Oh, right.
So if it's just one more than that, in the worst case, the tree must have an additional depth, especially if it's this binary tree, right? So recall in the pumping lemma for regular languages, we use this letter P over and over. What was the P actually corresponding to? I didn't remember. It's been a minute. The P in the pumping lemma for regular languages corresponded to what? Yes, but exactly. But we kind of abstracted away by calling it the pumping length, but it corresponded to something. It was the number of states, right? So some computation repeated a number of states, right? So we set the pumping length, quote unquote, to be the number of states. Here, we kind of want the pumping length, it's going to be a function of v and 2 to the something. So what we're going to do is say set p to be 2 to the cardinality of v plus 1. Now we're going to put the plus 1 in the exponent because that is greater than 2 to the cardinality of v plus 1, right? Let's just say that. Now this is less general. This is more precise, but this one will be more useful in a second. But it's okay. We can kind of overestimate the pumping length because it's just going to be generic anyway. But we want the S to be longer than this, quote unquote. Now when we actually do the proof, we just say let S be longer than pumping length P, and then you don't have to think about this 2 to the V plus 1. But we need to know the exact conditions of the long enough string for it to be the case that the parse tree has the height that we require. And do we agree at least with this? So if we agree with this, and this is sufficient, then setting P to this is no problem at all, right? And now we just need to explain, like, why can we set P to that? Why are we doing that conventionally? So recall in we're not looking at a version of the pumping lemma that is so general that's going to be able to perfectly characterize all the possible periodicity of the context-free languages, right? We have observed, first of all, long enough strings in context-free languages have this ability to be pumped over and over. But we're not trying to perfectly characterize how these repetitions occur. We're simply trying to get a lemma that's good enough for us to prove that certain languages are not context-free. So when we're looking about how things repeat, it is true that different non-terminals can repeat any number of times. Maybe a non-terminal repeats k times. Maybe it repeats up here, and then up here, and up here, and so on, right? So we're looking for just like one specific repetition that allows us to make restrictions, in fact, such that those restrictions are going to be useful in our theorem, right? So suppose we have a parse tree again. Okay. Suppose it's long enough that A is repeated many times. Maybe there's multiple repetitions of A throughout the parse tree. Maybe A repeats here. Maybe some other non-terminal T repeats like 3 times up here or something, right? But we're concerning ourselves with the last repetition of a non-terminal, right? Let's focus in on A is not just any non-terminal that's repeated twice, but the last non-terminal that's been repeated twice, right? So what do we know the height of this portion of the parse tree is? Forget how tall the actual computation is. What is the height of just this portion of the parse tree where the last repetition of non-terminals occurs? The max height, in fact.
Cardinality of v plus 1.
Correct. So just this part is cardinality v plus 1, right? So then therefore, what can we say that the length of Vxy must be less than or equal to B.
2 to the power of that, or
2 to the V plus 1, correct. But that's just our pumping length P, which is why we're using the plus 1 in the exponent and not the plus 1 in the bottom, right? We're making it less general, and instead of having 2 pumping lengths, we have to juggle, why, who cares? So let's just do this one, it's gonna be simpler. So here's how every pumping lemma proof outline is gonna go. Before we do that, any questions on why it's true? Why it follows from the pigeonhole principle, surgery on parse trees, what's actually quote unquote being pumped? Okay. Here's the proof structure for every pumping lemma proof. Assume to the contrary. L is a CFL with pumping length P. Now by pumping length P, we're really assuming that the parse tree, 2 to the V plus 1, whatever, who cares, right? But we can just call it pumping length P in the proof and abstract ourselves away. We don't have to deal with it anymore. Consider some S in L with the length of S exceeding P, right? Choose, for all cases, that S is equal to UV, X, Y, Z, subject to Vxy is less than or equal to P, and there's one more case we have to talk about. We have to make sure that we're pumping something not empty. So we say that Vy exceeds 0. Choose I and show that U, V to the I, X, Y to the I, Z is not an element of L. We follow those steps, we're going to get the, that's going to be basically the outline of how to pump a language, how to prove it's not regular. Excuse me, not context-free. Questions on the proof outline? The rest of today will simply be spent on some examples of like how do we actually demonstrate the use of this. So I'll tell you that the pumping lemma for context-free languages, unlike the pumping lemma for regular languages, is like if you make a mistake in the pumping lemma for regular languages, you might accidentally still be right. You might be able to wander your way back to a correct solution, but you'll just have an uglier proof. The pumping lemma for context-free languages, you're not going to be able to do so, and it's very likely that you won't be able to finish the proof correctly. So it's a much harder thing to work with, let alone the fact that that may be obvious because we're splitting the string not into XYZ, but into 5 pieces, UVXYZ, right? Another restriction here is that VXY is just something in the middle. Recall that when we did the other condition on the pumping lemma, it was at the beginning of the string. So you could just make the first P symbols all 0 or whatever, and that would always work. But that doesn't exactly work here now because this could be some substring somewhere in there, right? So which language should we prove first? Of course, the classic one. A to the n, b to the n, c to the n, n is a natural number. We prove such a language is not context-free, right? Assume to the contrary. That L is a CFL with pumping length P. Consider S is equal to what? What's a good choice of S to be in this language?
Nine?
9. What do you put 9?
Wait, no.
I'm asking for a string of A to the n, B to the n, C to the n.
A, B, 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 C, C, C.
But we wanted a function of P, right? If you recall the proof that A to the n, of A to the n, B to the n, what did we choose our S to be?
Oh, right. A to the P, B to the P, C to the P.
Yes. You don't yet know that string is going to work, but it's a pretty good choice, right? Why? First off, confirm for yourself that S is an element of L. Okay, good. And also confirm that the length of S is equal to 3P, which exceeds the length of P. We're good. It's long enough. Not only is it long enough, it also is an L. Okay, now let's peel back some of the layers a little bit and look kind of what's happening at the assembly level. We chose, P here is technically 2 to the V plus 1, right? So in fact, we chose just this first block of A's to be so long that the parse tree, that's the parse tree height here is going to have repetitions for each of these, right? So we have 2 cases for S is equal to UVXYZ, subject to VXY is less than or equal to P, and VY exceeds 0. Now, the thing with the pumping lemma for context-free languages is these cases, quote unquote, are very general and are not really like one case. They're really a collection of similar cases that we, without loss of generality, just kind of absorb into each other. So we'll call them a meta case. Meta case 1 is that both V, Y contain only one kind of symbol. So to illustrate this for you, what we really mean here is that there's like, all right, let's say our string is broken up like this. What we really mean here is there's actually several cases here. We mean that V and Y are both A's, V and Y are both C's, V and Y are both B's or both C's, or V is A's and Y is B's, or V is B's and Y is C's, for however that lines up, right? This is technically 5 cases. By the way, why can it never be the case, in this case, that if V and Y both contain one kind of symbol, that V is A's and Y is C's? Right? There's 2 of V and Y and 3 of A, B, C. So you would think it'd be 3 choose 2, which is 6. But it's not. I claim the case that V goes here and Y goes here can never happen.
So then with like how they're produced from the inside out, you wouldn't be able to like separate them?
Not quite. It's a pumping specific thing.
It's UV to the X, Y to the IZ. That means there's only one separation between V and Y. So if P
How
of
far away can V and Y be from each other?
1? Like,
It could be a little farther than that. It could be the case that X here is like length 20.
oh, X can be any length?
Yeah.
Okay.
Well, almost. Could it be any length? This is, again, not obvious, but VXY must be less than or equal to P. So we know that VXY as the substring is at most P from each other. The length of it is P. So the first symbol of V cannot be more than P from the last symbol of Y. But there are PBs here, right? So we know that, in fact, this A and this C are too far apart. So they simply cannot be, just because of the way we constructed the string, VXY cannot be, this far apart. So this case will never happen. It could be the case that VXY is here, or VXY is here, or VXY is here, or here, or here. But it can never be the case that VXY is like this long, right? What's the contradiction? What I should we choose? Give me an I. Any I that's not one. Yeah. Notice then that there are 2 of V comma Y, but 3 of A, B, C. So what do you know about UV squared X, Y squared Z?
In any case, it would be switchable.
Yeah, some letter is not going to be inflated, right? When you pump up, You're going to increase the A's or the B's or the C's or the A's and the B's or the B's and the C's, but never all three. So the number has an unequal amount of letters. So this is not an element of L, right? Meta case 2. If it's not the case, you want to make sure your cases are total. And if you have two cases, it should be the case that the second case is the logical negation of the first case, right? So if this case contains if both V and Y are only one kind of symbol, what is the second case supposed to be? What is the opposite of V and Y contain one kind of symbol? Yeah, and in fact, the and changes to an or through De Morgan's. Either V or Y, or both, contain more than one kind of symbol. This is analogous to us if we had, let's say, A, B, B, C, C, right? What this really means here is that, let's say, V is somehow here, maybe, right? Or V is here, or X is here, Y is here, or Y is here, right? In the sense that whatever that substring maps to, it contains both A's and B's, or both B's and C's, and same for Y, right? Consider I is equal to 2. Then UV squared X Y squared Z. What's the problem with that now? There's a different contradiction that's arrived here. If we inflate Vxy, what's going to happen? If we inflate V and Y, what bad thing is going to happen this time? It could be the case, for example, that the number V overlaps A's and B's, and Y overlaps B's and C's at the same time. So there is a small chance that when we pump up, the number of A's will equal the number of B's, which will equal the number of C's. That could happen. So we can't reach the same contradiction, but there's a different contradiction. This is also kind of a stringology thing and not a super...
Is it the concatenation? When we concatenate V to itself, it'll go into A, B, A, B.
A, B, A, B, exactly, right. Basically what's going to happen, let's say we pump up V, it's going to look like A, B, something like this, right? You're going to have a B before an A, right? If you pump a copy of this, at the appendage here, you're going to put the A after a B. But we know A's must come before B's, and B's must come before C's. So the contradiction is this will contain letters out of order. And thus is not an element of L. Since we have proven for all cases that for any way we could break S into U, V, X, Y, Z, we've chosen an I and shown that that's not an L, we can conclude that L is not a CFL. QED. Great, we have our first example of a non-context-free language, right? Questions on this proof? Any intermediary details? I will say, of all the proof styles, especially that we'll do in this class, I think this pumping context-free languages requires the most creativity and is very difficult to get correct. So it's not necessarily expected that you should follow along this proof and be able to come up with it on the spot. That's not something that's important. There are many better ways and worse ways to write this proof. We could have, for example, converted meta case 1 into 5 cases, meta case 2 into 3 cases, maybe 4, right? And then done like case 1, case 2, case 3, but they would have looked all the same, right? So writing it this way, it's not obvious how you would simplify it, but just know that it's correct. And that's more, verifying the proof is more important as your job than figuring out how could you have come up with the proof. So that's kind of the goal here. Questions on that? All right, let's do another one. So consider assembling one a to the I, b to the j, c to the k, such that I is less than equal to j, which is less than equal to k. I claim such a language is not regular. Not context-free. Assume to the contrary. That L is a CFL with pumping length P. Consider S is equal to what? What's a good choice of S? There are many languages we'll see an example today where it's easy to choose a really bad language. Really bad S, and the proof doesn't really work out. So if you make a simple choice of S, it can simplify the amount of cases you can have. Really more like that if you make a bad choice of S, the proof will not be completable, right? Because it's very easy to choose a string that's accidentally pumpable, but you want to choose a string that's not pumpable. So what's a delicate string that happens to be in this language that you would suspect that a perturbance to the string would bring it not in the language?
A to the P, B to the P, C to the P plus 1?
Not necessary.
Or C to the 2P?
That would also be okay, but actually we just need this. Right? Here's kind of why it's delicate, right? If you pump up C, you don't reach a contradiction. So similarly, if you pump down A, you don't reach a contradiction. So you need to choose I very carefully where your VXY is going to be so that you pump up or pump down accordingly, right? Notice that S is an element of L, and the length of S exceeds a P because it's on 3P, right? We have two cases. Consider the meta case 1. It's going to be the case that V, and I should say here, hold on. For all cases, S is equal to U, V, X, Y, Z, such that VXY is less than equal to P and Y exceeds 0. We could say our meta case 1 would be similar to the other meta case 2, which is that either V or Y contain more than one symbol, right? So let's say one of those cases is of the form V, we'll call this U, X, Y, Z, something like this, right? So let's say that either V or Y contain more than one symbol, right? So V, for example, in this picture overlaps at the crossing point between A's and B's. What's the contradiction there? Well, choose an I first. Give me an I. This one's easy, actually. Consider I is equal to what?
Negative.
Can't choose negative. You have the pump, right? It's got to be some number of strings. So the math on strings has to be natural numbers, yeah. It's early, it's okay. I'll help us out. It's 2. Then U V squared X Y squared Z has what property?
But it's the same thing as before.
Exactly.
It contains
Yeah.
more than one symbol.
Exactly. Has letters out of order. So we know that this is not an element of L. Meta case 2. Both v comma y contain one kind of symbol. I can even say each. So what this means here is like v and y's are both a's, they're both b's, they're both c's. One's a's, one b's, one c's, and so on, right? So we have let's just list out the cases. If v comma y are all a's, consider I is equal to what? So let's say that v and y are both a's, so they're both here, right? They're all in the first p characters. What I should we choose?
2.
Let's see, if we pump up, we'll have more a's than b's. So we will reach a contradiction. Consider I equals 2. So uv squared x y squared z has more a's than b's. Now what if v comma y are all b's? So that case corresponds to, they're right there. Consider I equals what?
2 still works.
Yeah. In fact, for this one, 2 or 0 would work. If you pump down, you have less A's than B's. You have less B's than A's. If you pump up, you have more B's than C's, right? So uv squared x y squared z has more B's than C's. Okay. Subcase 3, Vy are all C's. Consider I is equal to what?
0.
Yeah. So uv squared x y squared z has what problem?
Less C's than B's.
Okay, what if v is b's and y is c's? Consider I is equal to, now where would this look like? We would put v here and y somewhere here, right?
I equals 0, you would have more A's than B's and C's.
We pump down, let's just say we would have, has more A's than B's. Okay. And our last case is V is all A's and Y is all B's. Consider I is equal to what?
2, and then more B's than C's.
Okay, why can the case V is A's and Y is C's not happen?
Same reason it could happen with the distance between those P.
Exactly. If this is P apart, you can't have V all the way over here and Y all the way over here. Because we've chosen our string of sufficient length. Now, had we done something terrible like chose S to be P over 3, P over 3, P over 3, something like that, that would not hold. And so we'd have to consider some horrible other things. Not applicable. But in all cases, we see u, v to the I, x, y to the I, z is not an element of L, so L is not pumpable, so it's not a CFL. Now let's take a second to look at this proof from a distance. This was really annoying, right? It was a lot of casework. You have 2 meta cases, and then those cases are broken up. And we kind of have to break it up because you have to choose different I's. Now, you could figure out a way to word this better, but it might be slightly more confusing. For example, this case and this case basically are the same, because you could just say if V is A's, just ignore where Y is, pump V up, you're still gonna reach a contradiction no matter what happens to Y, right? So you could combine this case and this case, and likewise you can combine this case and this case, right? You would still need this case. So you could make this 3 cases, and then it's like, well, then you gotta think and argue about the cases and so on. So just to illustrate, sometimes applying the pumping lemma for context-free languages can be quite a lot of casework, right? Questions on this one? Yes?
Why is it that y has to be greater than 0 here, but it's vy over there?
Oh, I just made a mistake, that's all. Thank you very much. Perfect. Yes, something non-zero has to be pumped. So V can be 0, Y can be 0, but they both can't be 0. Excuse me, by 0 I mean the empty string. More questions on this proof? Let's do one more. So of the languages that we proved not regular, some of them we were able to prove are context-free, but some of them we weren't. So we've already proven languages to not be regular, be the pumping lemma for regular languages. Name one of those languages that we proved was not regular via pumping, but we were not able to give a context-free grammar for it. There's actually 2. This is a memory thing more than... I'll tell you, the 2 languages were 1 to the n squared, right? If you can recall that one, a unary language. And the way we pumped it is, recall we showed the pump was in between 2 perfect squares, so it could not be either of them, right? If you think about pumping the context-free, if you think about what the proof would look like for the context-free language, it's gonna look the same. You're gonna have the same problem where the pumped string is gonna be in between 2 things. And why that is, we'll kind of illustrate next time. In fact, you can take the pumping lemma for context-free languages and pretend it's only on regular grammars, and you can derive the pumping lemma for regular languages as a special case of that for context-free languages. It's also true that kind of follows from the fact that every regular language is context-free. So if you prove something is not context-free, it of course cannot also be regular, because every regular language is context-free. So that was one. The other one, which we're more interested, is WW, such that W is in sigma star. Right? Recall we were able to give a PDA and even a context-free grammar for WWR. There was no problem with that. Why? You push W into the stack, and as you pop it out, you make sure it reads the same. But it comes out of the stack in reverse order, so you're good. But this, you can't arbitrarily like push it into the stack and then like rotate the stack around and then have it come out. That would not be possible. So, don't know about that one. Well, it's not a context-free grammar because there's no context-free grammar for it. It's not a context-free language. Let's prove it. There's no PDA for it either. Assume to the contrary. L is a CFL with pumping length P. Consider S is equal to. Now, there are plenty of bad choices of S, right? Let's come up with some. Choosing the S for this language is actually quite delicate. So let's hear some suggestions for strings S, such that S is in the language and S is longer than length P. Give me any suggestions. Name any string that has that property.
W power P, W power P.
For what specific W? Make W, choose some W out of it, zeros and ones.
0, 1, 0.
Yeah, so let's try some awkward choices. 0 to the p, 0 to the p. Turns out that that one will not work. You can actually pump such a string and you won't reach a contradiction. Why? If your pump is of even length, as long as you have an even length string of all zeros, that's technically still of the form WW. So this one won't work. And it takes a couple tries to come up with a good string. What's another choice of S you may consider?
Zero P, 1P, 0P, 1P.
That's going to actually be the correct choice. 0 to the p, 1 to the p, 0 to the p, 1 to the p. But let's consider some other bad choices. So let's try 0, 1p, 0, 1p. Right? That's another choice. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Right? This is also a bad choice because you can, well, it's not a bad choice, but it's like you'll never complete the proof with it. Why? Because you can still pump it. So what we mean by pump it is you can take a substring of it, carefully chosen. You need to show that no way you can break up the string, you pump it, no matter how you break it up. But there is a way to break this up to pump it. You can actually choose like a substring. You can choose a v to be 0, 1 and y to be 0, 1, and a pump of that will be perfect. It'll still work, right? So this one doesn't work for that reason as well. And there's a few other ones you could try and do so. Now, why this one works, you'll have to just see in the proof. Because this is basically, I think, one of the only strings you could choose. I can't think of another. And it's difficult to find such a string, I think. But let's just proceed with the proof. For all cases, first, if S is this string, observe that S is an L, okay, good, and the length of S exceeds P. Also good. For all cases, S is equal to UVXYZ, subject to VXY is less than or equal to P, and VY exceeds 0. We have really two cases, which is that, we'll call it meta case 1. VXY is entirely on the left or right half. So what we mean by that is that if we have 0, 0, 1, 1, 0, 0, 1, 1, that VXY is somewhere here. Or VXY is somewhere here. It's just not over the middle line, okay? It's all the way in the left half or it's all the way in the right half, right? By the way, let's just assume the pump is even, because if the pump is odd, we reach an immediate contradiction and we're good. So let's just suppose that the pump string is of even length. What's our contradiction? Well, first let's say consider I is equal to 2. Let W1, W2 be such that UV squared X Y squared Z is equal to W1, W2 with W1 equal W2, the lengths, but not the strings. Right? That's just to help us make the argument. If we were to pump up and consider the halves of the strings, what's the contradiction? It relies strongly on this choice of S and how we were able to pump.
If we consider I greater than 1, it will shift that like midpoint to the left. If it's to the left, then it's been shifted into the 1 to the power P. So the first character in W2 is 1, while the first character in W1 is 0. So
exactly. If we're here and we inflate this, W1 is going to begin with zeros, but there's going to be a 1 that's going to be pushed over here, right? So either W1 begins with 0, while W2 begins with 1, or W1 ends with 0, while W2 ends with 1, right? If you inflate here, you're gonna push a 0 over there. So the first half of the string will now end with a 0. It'll be 0 to the p, 1 to the p, and a couple zeros. Even if you pump the 0 or the 1, doesn't matter. It's gonna push it over there, right? So when you push it over there, W1 is gonna end with zeros, while W2 is gonna end with 1s, right? So just to illustrate that, that would mean that the halfway point was there, for example, and that 0 is pushed over the line. Either way, so W1 does not equal W2, and u v squared x y squared z is not an element of L. Okay, we're done with that meta case. Meta case 2. So what's the logical negation of vxy is entirely on the left half or the right half? Yeah. Vxy straddles the middle. Contradiction here is relatively simple but hard to find. Consider I is equal to 0. Then uxz is equal to 0 to the p, 1 to the k, 0 to the j, 1 to the p, with both k, j not equal to p. So one or the other could be equal to p, but not both, right? If we pump down, we've removed something from those, right? So it could be the case like v is empty and then we didn't actually remove anything, or y is empty and we did remove something, whatever. Or y is not empty, we did remove zeros. But either way, we have removed some number of 1s, some number of zeros. Maybe no zeros, but we removed 1 once. We didn't remove nothing. Something was removed, right? But what's our contradiction? Why is this not an L? It's kind of tough.
One of k and j doesn't equal p, so
That's basically it.
Actually,
It's hard to argue. It's really hard to I mean, intuitively you visualize the string and you get it. But how do you say it's not like W1, W2, and then we're like, where's my...
I guess you could say there's two cases, k equals j, k doesn't equal j. If k is equal to j, then that means that the midpoint stays the same. Then obviously 0 to the p, 1 to the k doesn't equal 0 to the j,
Correct.
1 to the p. And then if they're not equal, then the midpoint shifts, so it'll be the same argument as
Exactly. Now, the way that this is traditionally written, with that in mind, is that we say this kind of hand-wavy sentence, but that's the more appropriate detail I should be putting here. We would say, but 0 to the p, 1 to the k, 0 to the j, 1 to the p is an element of L only when k is equal to j is equal to p. So only when that happens can a string of this form be in the language WW. But we know that k cannot equal j. I mean, both k and j cannot equal p. So the only way that they're in the language is if they equal p, but they won't be, right? Contradiction? So we've seen for all cases that u v to the I, x, y to the I, z is not an element of L. So L is not a CFL. QED. Done. Questions on proving that WW is not a context-free language? Excellent.